So we have work. And I'm just going to read the definition to you. It's going to be in your textbook, but mostly I'm going to draw a picture to explain what work is. So backing up to potential energy, it's the capacity to do work. So what is work? Work is energy used when a force moves an object through a distance, right? If I have a box and this box is in front of me and I push the box, I'm exerting a force. The box then moves through a certain distance in the direction of motion, then it's said that I have done work on the box. In moving the box from point A to point B, that is the physics definition of work. I have to be exerting a force, and then it has to also move through some distance d. And then what do we have? We have this situation here. So here I have some box. Just going to draw a little box, nothing special. I'm exerting some force. I'm just literally standing here pushing this direction. And then the box ends up in some final position. So I'm putting a little dot there because some time has passed and I've moved it here. Now, how far did the box move? Well, you can pick the trailing edge to the trailing edge or the leading edge to the leading edge. Either way, if you pick a consistent place, it's going to move through some distance d to get to its final destination. So the trailing edge of the box to the new trailing edge of the box moves through some distance d. So if you push a box with a force F, and then don't forget, once it's moving, you're still pushing on it with a constant force F. See this equation I'm about to write? It's assuming that the force that you're applying is a constant force that doesn't change. If the force changes, like if you start pushing harder or softer, then you have to use calculus to handle a more complicated situation. We're not going to do that here. We're going to assume the force I'm pushing is a constant force, it never changes, and then the box moves through some distance d. All right, and then once we have these two conditions here, then we say that the work done on the box is equal to the force multiplied by the distance. Now I have to explain a few things here that are very important. All right, the distance. The distance is in meters, which is m, right? Now I'm telling you the units that we have to use so that when we calculate things, we have to have them in the proper unit. And then you know what unit you're getting, what you're calculating here. So the distance are in meters. If the distance not given to you in meters, then convert it to meters and then stick it in here. The force is a unit in physics we call a Newton, right? And we call that capital N. So you might be thinking pounds of force in the English system. In engineering and science, we use newtons. You can do a straight conversion from pounds of force to newtons. Not hard to do, but we don't want to deal with pounds, okay, ever. We want force is going to be in newtons and distance is going to be in meters. And so when you take a force in a given number of newtons and it's acting on a body that moves through a distance d in the same direction of the motion, then the work is given in a unit, which is called a joule, right? And a joule is the unit which we just abbreviate J. Now, most people here in the beginning have never really heard of a unit of a joule, but actually you do have some sort of experience with joule. You may have heard of a watt, right? A 60-watt light bulb, a 120-watt light bulb, something like that. A watt is equal to 1 joule per second. So you see, the watts that you've heard of throughout your life, like this many watts, that many watts, that is actually not a unit of energy, it's a unit of power. Power is energy flow. It's joules per second. So here I have lights hitting me from everywhere. Let's say that we had a 60-watt light bulb. Then every second, it would be, that's 60 more joules. If it's a 60-watt light bulb, that second. Next second, 60 more joules hitting me, 60 more joules hitting me, 60 more joules hitting me, 60 more joules hitting me. You see how that goes? So when we use the word watt, that's a shorthand way of telling you how much energy is coming per second. And when you have a 60-joule light bulb or 60-watt light bulb, it's 60 joules per second, because 1 watt is 1 joule per second. So it's kind of a crash course in units here, but I just don't want you to get confused with watts and joules. Joules is just how much energy you have available to do something. Watts is like a continuous flow of energy over time, every second, that many more joules, and so on. So the unit that you calculate this work is in joules. We're also going to learn in a few minutes that the unit of potential energy is also in joules, and the unit of kinetic energy is also in joules. So kinetic energy, unit of joules, potential energy, unit of joules, work, unit of joules, they're all in the same unit. They're all in the unit of energy. That means they're all very closely related, and that's why I can't break this long lesson up, because they're all interrelated. If I broke it up, you would never see the continuity between them. All right? So, unit of joules, force, distance. Now, another thing I need to say, I wrote this as a dot here, force times distance, but this is a dot. If you take a physics class, you will learn that this works great if the force is lined up in the same direction as the distance, but if the force is angled at some angle, then it's not a straight multiplication. Basically, the dot there comes from the dot product in math. I'm not going to get into it now, but basically the dot product handles the situation if the force is angled to some angle relative, like if the box is moving like this, but you're pushing down at an angle, the only force that is really contributing to the work is the amount of the force acting in the direction of motion. So if you have a force that's acting down at an angle instead of straight across, then you need some way to figure out how much of that force is acting in the direction of the box moving. And the dot product from math, or from physics, is what handles that. So we're going to avoid all that, because in this little example I drew the force acting in the direction of motion, so it's just a multiplication. But I just want you to know that if the force is at an angle or something else weird is happening, then you need to basically calculate the percent or the amount of force in the direction of motion. That's all that matters for the work. So basically, when I move a box, the amount of work that I do on that box is only related to how much force I push in the direction that the box moves, multiplied by how far the box moves in newtons or in meters, and then times newtons, and you get a unit called joules. All right, so that is 1/3 of what we really need to cover. This is the concept of work. Now we need to cover the concept of potential energy, which we talked about, but we're going to talk a little more about it here now. So potential energy. All right, potential energy. We already gave kind of an intro here, and the intro was essentially that potential energy is the potential to do work. That's literally the definition, the capacity to do work. This rubber band is exerting a force on my fingers. And because of that, if I were to let it act, if I would let that force act on my fingers and pull them together, then there's a force and there's a distance my fingers moving, and so work is being done on my fingers, right? By the force, basically by the molecules inside of this rubber band, the forces that are going on in there, right? So potential energy is when things are not moving, I have the potential to do work. When things start moving, then I'm doing work. Even whenever I get down to the point where my fingers aren't moving anymore, now I'm in a relaxed state, the force has done its job, it's acted on my fingers have moved through a distance, and I've basically converted the potential energy, which was very high in the beginning, I've converted it as my fingers have now stopped. I've converted it into work because my fingers have now moved through a distance by a force. So you see how they're tied together. The potential energy is what's happening before the motion happens. As the motion happens, you see my fingers are no longer moving anymore. So you would think nothing's happening, but what's really happened is the potential energy that I had is converted into work. That's why the units of all these things are the same. They're just sort of different ways of thinking about the same thing as the process happens. Now, I've talked about rubber bands. Rubber bands are great, but in the concept or the discussion of potential energy, I want to transition to talking about gravity, because it's actually much more closely aligned to the electric force. So in the electric force, you have electrons and protons attracting or repelling each other. Actually, the equations that govern how the force of the electric force, it actually is very, very similar to the force of gravity. We all have an intuitive feel for gravity and energy with gravity. All right, and so we're going to use that because we're going to use that our everyday experience to help us translate to what's maybe happening at the atomic level, right? So let me ask you a question. I'm standing on the ground right now, all right? If I had the situation of me standing on the ground right now and compare it to the situation where I climb up on a ladder or on the top of a very tall building, which of those situations would have higher potential energy? Well, right now I'm at ground level. I really can't fall, I can't really hurt myself, so I have a low potential. Maybe I even have zero potential energy because I can't really I can't really do, I guess I could crush myself to the ground, but that's it. But if I'm at the top of a building and jump off, then I have a very large potential energy right before I jump, because if I were to jump, I can convert all of that into motion. And so I have a high potential energy the higher I am above the ground. And I keep saying it like this, I'm trying to drill it in your mind, because we have the same thing happening with electrons. Electrons that are far away from an atom, far away from the nucleus, have a higher potential energy, because those electrons can come crashing down through the attractive force with the nucleus, crashing down into a lower energy state. And that happens all the time in chemistry. Like literally every chemical reaction is involving that kind of stuff. So we're going to use gravity as a kind of like an analogy with what's happening with electrons. So the higher up you are on a ladder, the more potential energy you have. The higher up an electron is away from an atom, the higher the potential energy that electron has. So let's go over here and talk about this. We have this situation. We have really two situations. Here is Earth, right? And we're going to have another situation over here I'm going to draw, which is also Earth. Right? It's basically the same situation that I kind of like verbally asked you about just a second ago. So let's talk about situation number one. Here is a box. I'm going to put it right here. This box is some mass m, right? And then I'm going to have another situation where it's right here, closer to the ground. Another mass m. The mass of this box is exactly the same as the mass of this box. It's like, I don't know, 5 kilograms or whatever it is, 10 kilograms, right? Which of these has the higher potential energy? We already talked about it. This one has a higher potential energy because if I let it go, it's going to come crashing down with a higher speed and impact the ground. And if I let this one go, it's also going to hit the ground, but it's not going to be traveling as fast. So it didn't have as much potential energy to begin with. So to continue filling in the blanks here, this is some distance, h, off the ground, like this. And this is some distance, also h off the ground. Of course, this h is bigger than this h. All right. And we already said that this one is a higher potential energy. And we already said that this one here is a lower potential energy. If we could calculate the potential energy in this situation and compare it to the potential energy in this situation, this one's going to be lower and this one's going to be higher. And that's exactly what we do. So what we say is that the potential energy, and this is an equation you'll learn in physics, but we're learning it here as well, is just the mass times the gravity, the gravitational acceleration of the planet you're on, times the height above the ground. All right? Now, there's a lot of gotchas that go into this. I don't want to get into all the gotchas, but basically it assumes gravity is constant. As you get farther away from the planet, technically the gravitational force gets less and less. So this equation holds for everyday situations close to the surface of the Earth. But if you're in a spaceship and you move 6,000 miles that way, then yes, the gravitational force is a little different. So this equation becomes more complicated. But for the purposes of us talking about this to understand energy, it's perfectly fine to just say that potential energy is mass times gravity times the height. Now, what are these units here? Well, the height, you might guess, is in meters. I'm just going to put m right here, same meters we used before. And the gravity is, since this is in meters, and this is the gravitational acceleration, so it's meters per second squared. Remember, you may or may not know, the units of acceleration is, the units of speed or velocity is meters per second. But we're not talking about that. We're talking about acceleration. How fast does something accelerate? How much does it fall if you drop it? The gravitational acceleration, that's meters per second squared, right? So that's that unit. And then this mass is in kilograms, as I told you before. I think I told you, maybe I verbally told you, kilograms. If you have the mass in kilograms, the gravitational constant acceleration, meters per second squared, and the height in meters, then what do you get for the potential energy? You also get joule. So I'll put joule, which is a unit of J. So notice that when we calculate the potential energy in these situations, we get a unit of joules, assuming we use these units here. If you don't have the units given to you in the problem like this, then you convert them. There are other ways to handle it, but I would just convert them always to these basic units. You get joules. Work is force times distance. You also get a unit of joule. Now, why are they the same unit? Well, it's because if you think back to the rubber band, or if you think back to this, right now the rubber band's exerting a force on my fingers. If I allow my fingers to come together, the force is doing work on my fingers because it's force times distance, right? And so the potential energy I had, let's say I had 10 joules of potential energy. And then if I were to calculate force times distance, when I get to 0, maybe I've done 10 joules of work. And so the 10 joules of potential energy got converted into the energy of work, which is essentially the 10 joules. So everything balances. You have to have conservation of energy. All right. Now, if you want to think about it in terms of gravity, here you have a higher potential energy, maybe 10 joules or 100 joules, m times g times h. And then whenever you're at a lower distance off the ground, you have a smaller potential energy. And this just basically means that if I let it go, then you're going to have a higher motion, higher energy conversion from potential energy to energy when you hit the ground as it speeds up, and you'll have less conversion there because you started with lower potential energy. And again, I'm going to say it one more time. If you think of this being a nucleus of an atom, the higher electrons are in a higher potential energy state than the lower electrons. We actually call them energy levels. Later, we'll talk about energy levels of electrons. The ones that are closer are in a lower energy level. The ones that are higher are in a higher energy level. Just put the word potential in front of there. We could say the lower electrons are in a lower potential energy level, and the higher electrons are in a higher potential energy level. In general, electrons like to go down to the lowest potential energy, just like when I drop this pen, it likes to go down to a lower potential energy. Throughout this class, I'm going to constantly say nature likes to go from a high energy state to a low energy state. That's just the way the arrow of time works in our universe. In your mind, I want you to translate that as, oh, all he's saying is things like to fall down. So when you say, why do things fall down? The answer we don't really know, but the answer is because the universe likes to go from higher energy states to lower energy states. So if I hold this thing in a high energy state, it's going to spontaneously travel to a lower energy state because here is closer to the ground, here is higher to the ground, higher from the ground. So that is potential energy. Now we need to talk about the last of the important ones here, which is the kinetic energy. And actually, before I get to the kinetic energy, I'm just going to tell you some things that I've said in words, but we're going to talk a little bit about chemistry on this board here. I'll just say systems. Try. In general, I mean, there's always counterexamples. Okay, generally try to go to lower energy states. Right? You can think of a roller coaster. I'm going to draw a picture. It goes up to the top. It likes to go down. It picks up speed, then goes up and slows down, then down like this. That's trying to go to a lower energy state. So for instance, if I have some kind of atom here, you know, here's a proton right there. You know, here's a neutron, right? And I draw another atom with the same nucleus. Here's a proton, here's a proton, here's a neutron, here's a neutron. I know we haven't talked about the structure of atoms, but I think you all know from 5th grade or so, that the nucleus is where the positive charges are located along with what we call neutrons, which are no charge at all, but they have mass. Those are all in a very tiny, we're going to talk about how small. It's an incredibly tiny part of the atom in the very center called the nucleus. And surrounding it, usually we draw electrons orbiting, but you know, we're going to talk more about that later. They don't really orbit like that. They don't really look like planets. We're going to talk more about that later. Electrons, protons, they're all different than you think. But you can think about them going around them for now. All right? So if we have an electron right here, and maybe we have another electron on the other side, and they're essentially in the same orbit like this, which again, I'm telling you right now, they don't really orbit like this, and we'll talk exactly why later. But this is a higher energy state than a situation like here, where you have electrons that are closer to the nucleus. Right? So this is called a higher energy state. Higher energy. Whoops, if I can spell energy right. So I can say high PE. High potential energy, because they're farther away, right? And this is lower energy. Lower PE. And in general, system likes to go this way. So nature goes like this. From this state to this state. Not always, but because there are other situations. In lasers, we try to pump the electrons up to a higher energy for reasons we'll talk about when we talk about lasers. And it makes the light, if you could do that to a bunch of atoms at once in a certain way, you can make the light very focused. Sometimes we try to pump the electrons up. Sometimes we add heat to a system to get the electrons to get up to a higher energy to start, then the chemical reaction can then start. There's a lot of details there. But in general, is the big picture of the driving force of nature in the universe. Generally, things like to go from a high energy state to a low energy state, just like things starting from a high energy state here, they spontaneously fall to a low energy state. But we don't look at atoms every day, so we don't see that, but that is what's happening to those electrons. They're trying to go to a lower energy state. And that basically leads to chemistry. When the electrons are moving, or transferred between one atom and another, and then the forces are acting to pull things together and bond them, that's what we call chemistry. Breaking bonds and forming bonds is chemistry. So later on when we talk about chemical bonds, we talk about, two atoms coming together and sharing electrons, and then there's a force there kind of holding it together. That's a bond, right? All of those forces are acting basically like this rubber band kind of force. At a microscopic level, they're all pulling on things and holding them in place. So when we, in some chemical reactions, when we release heat, that's energy coming out of the reaction. Or maybe some reactions we have to add heat. Heat is basically energy that we're adding, making things vibrate. We have to add energy to the system. So all of the stuff that we're going to talk about in chemistry is very reliant on understanding these terms in physics. Right? Last little example I'll leave you with before we switch over and talk about kinetic energy. Let's talk about burning. When you, in general, burn something, you take some heat, like a match, you add to it wood or paper or whatever it is you have there. You have to add to it oxygen, which comes as a molecule bonded to itself. There's energy there because it's basically bonded to itself like this. And what do you get? Because inside this wood is, there's hydrogen in here, there's oxygen in here, a little bit, and there's also a lot of carbon in here. And whenever you do all these things, some bonds are broken between the molecules in the wood. Bonds are broken to split up this oxygen. Everything gets rearranged, and what do you get as basically an output is CO2 plus H2O. And there could be other compounds here too. I'm not writing them all down. Plus heat comes out, plus light comes out. Right? But I guess what I'm trying to tell you is that these molecules that are formed at the CO2, the carbon dioxide, and the H2O, these are in a lower energy state. Lower energy state than what? Than the energy state of these up here. And then you say, well, what are you talking about, lower energy state? What are you talking about? I'm saying that every molecule of this wood has carbons bonded in long chains. That's what it is when you zoom into woods. There's also hydrogen in there, and there's a long chain. You look up what wood is made of, in actual chemical formula of everything in there, there's long chains of organic structures there. And in this oxygen, it's one oxygen atom bonded to another. Well, they're bonded and they're being held together by a force, just like this rubber band. That represents potential energy. There's potential energy in there because the bond between the oxygen atoms is there and it's holding them there. There's potential energy in the wood because all of the long chain of carbon and hydrogen that's there, they're also bonded. There are little rubber bands in there, right? Then you put a match to it and you give it a little bit of energy to break some of those bonds. Then you have some freely floating oxygen atoms, not bonded anymore, and freely floating carbons, which come from the wood. And then what happens? They all try to recombine. And how do they recombine? Do they come back and make wood and more O2? No, they don't. Some of the hydrogen from here gets bonded to the oxygen. It makes water. Some of the carbon from the wood gets bonded to the oxygen with CO2. And then in addition to that, more heat is created, which is then allowing more wood to be broken down because this heat comes back in and feeds another little piece of wood right next door. And then light comes out. And the light comes out because of the electrons moving around. When the electrons jump up and down from their orbits, like we talked about here, when an electron starts from here and goes down, it loses energy. And what happens when it loses energy? A little photon of light comes out. We see that in a campfire. But these molecules that are formed are not the same as the ones you started with. And that's because these are in a lower energy state. What do I mean by a low energy state? I mean, if you add up all the bonds that are here and the strength of the forces that are there, you end up with a lower potential energy than the situation you had to begin with. Nature is trying to go to a lower energy state. I'm going to say that a billion times throughout all of these lessons. When things are broken apart and they're allowed to recombine, they're going to recombine into the lowest state that we can see. And if you were to add up the energies of all of these bonds that are here, which we will do later, and we add up the energies of these bonds here, and we tally it all, we're going to figure out that these are more stable molecules because they're in a lower energy state. It's just like dropping this box, and then it gets down lower to the ground. This is lower energy. These molecules are lower energy. All right. Now, there's a lot of details that I haven't covered, of course, but that is the gist of it. That's the most important thing. So we have talked about work when things move. We have talked about potential energy when things are higher or lower down to basically to a force that's pulling on it, because don't forget that acting on this box is some force due to gravity, call it F sub g, and then on this box is also some force due to gravity, right? And as it moves down, it goes to a lower energy state. So now we need to talk about the third important thing here that we can then tie everything together, and we call it the kinetic energy. Right? Kinetic energy. Kinetic energy is the energy of motion. So I'll just say the energy of motion. So whereas when the rubber band was stretched, there was potential to do something, right? But if I like take a marble and put it in here and like shoot it across the room, the potential that was stored in the rubber band is then converted to motion. Kinetic energy is the energy when things are moving. Potential energy is the potential to do work or to translate to energy when things are not moving. There's nothing moving here, but there's the potential to move. Once things start flying, then you have kinetic energy. That's the energy of motion, right? And so the kinetic energy is 1/2 times the mass times the velocity of the object squared. So the kinetic energy depends on the mass of the object, but it also depends on how fast the object is going. The units here, the velocity is in meters per second, the mass is in kilograms, the same units as before. And when you take a mass times velocity times 1/2, then you get a unit here. What do you think? It's joules. So again, J. Same exact unit as before. And that is because if I take this rubber band, right, and I have, let's say, 10 joules of kinetic energy. Nothing is moving, but this is the potential. If I could convert all of this potential energy into the energy of motion, and I fling it across the room, and I could look at its speed immediately when it left my finger, and I took its speed and multiplied v times v, speed squared, times the mass of that thing, times 1/2, I would get 10 joules of kinetic energy. Because all of the potential energy that was in that tension and the pulling that was there, it would be converted into the energy of motion. That's what we say we have a law of conservation of energy. Energy is really not created or destroyed, it's just changed from one form to another. Whenever I have this box up here, there's a high amount of potential energy, but when I let it go, the potential energy is converted to kinetic energy because it is moving at a high rate of speed when it hits the ground. So the best way to really demonstrate this or talk about it is to talk about a roller coaster. So here's a roller coaster, something like this. So what you do is you start out on the roller coaster and you get to the very high end over here. And let's say you're in, let me switch colors. Let's say you're at this position. We're going to talk about what happens when you're at this position on the roller coaster. And then we're going to talk about what happens when you're on this position on the roller coaster. And then we're going to talk about what happens when you're on this position way at the very end of the roller coaster. Of course, the roller coaster is moving this direction. It's going like this, right? So what's going to happen here at this position? What do we have? Well, the ground is right here. So how high are we off the ground? We're the maximum height off the ground. This is going to tell us how high total of an energy state we're in. We have the potential energy is in the highest position. Why? Because potential energy is m times g times h, mass times the gravity times the height off the ground. So in this position, we are the highest off the ground, so we have the highest energy, mgh. I'll just put m times g times h. H is the biggest right there, right? Now what is the kinetic energy here? The kinetic energy is 0 because I'm not moving. Right at the moment when I stop, right before I go over, I'm not moving. I have no motion, no kinetic energy. But I have a maximum potential energy. You need to start thinking in terms of energy. I have the maximum amount of energy. That is all the energy stored in that system at the top. And it all must come out somehow as this thing goes down the roller coaster. Now what's going to happen is this thing is going to get to this position, right? Which means the potential energy has gone down from here because I'm closer to the ground. My mgh is, because h is now lower, potential energy has gone down. But at the same time, the kinetic energy, that has increased. These are what my arrows mean. Potential energy has gone down because I'm closer to the ground, but I've picked up speed, so kinetic energy 1/2 mv squared is higher. I'm going to do the same thing here. I'm going to get to a local maximum here, and eventually, I'm going to slow down, and I'm going to pick up speed again, and I'm going to get to the bottom. What's going to happen at the bottom? The potential energy is going to be 0 because I'm sitting on the ground. There is no h. H is 0, the height. But the Ke, the kinetic energy, is highest. So you see at the top of the roller coaster, the potential energy is the highest, but at the bottom of the roller coaster, the kinetic energy is the highest. Because at the bottom is when all of that potential energy stored in the system has been bled down to 0, no more potential energy. Things try to go to the lower energy state, but all of it was converted into speed. And eventually you slow down with the friction on the tracks and all that stuff, but just forget about friction now. That's going to be the highest speed, highest kinetic energy. So basically, energy that was stored by climbing to the top of this thing, it was 100% converted into kinetic energy. No more potential energy. It got put completely to kinetic. If I had 100 joules of potential energy here, and there's no other losses due to friction or wind or anything, and it was 100% converted, then it would have 100 joules of kinetic energy at the end. It would all be converted from one form to another, from potential to kinetic. All right? And this is really the punchline of this lesson. Yes, we have a couple of problems I'm going to do at the end, but this is the punchline of the lesson. This part in the next couple minutes, hang with me, because this is literally where it all comes together. And I'm sorry to try to build it up too much, but I'm trying to get your attention because it's really, sometimes people fall asleep, and I want you to pay attention to what we're about to say here. So far we've been talking about roller coasters. We've been talking about kinetic energy, 1/2 mv squared. That's the energy of motion. We've been talking about potential energy. When things are high off the ground, they have high potential energy. And then we talked about the energy when something is moved and it gets to a new stopping place, then there's work done on it, and you can convert potential energy into work done. Even after the object has stopped, you've done work on the object. There's no motion anymore, but that potential energy can be converted into a kind of a new kind of energy called work. Now, all of the stuff we've been talking about has always been about gravity. And so now I need to tie it together. Right? This is not a physics class, but we can learn a lot by looking at these things, right? Let's take a look at gravity. And we're going to compare this to the electric force. Now, I've told you that the electric force is millions and millions and millions of times stronger than gravity. That is true. However, the equations for gravity and the equation for the electric force, they look really, really similar. Let me show you what this is. The force of gravity between any two objects, like two apples or two planets or two anything, right, is just what we call the gravitational constant G multiplied by mass number 1 of object 1 times mass of object number 2, and then it's going to be divided by r squared, the distance between the objects, right? So if I have basically two objects here, and this is, m1, and right here, this is m mass number 2. It depends on the masses of the objects, and gravity is always attractive, right? So there's going to be some attractive force right here, and it's going to be F, essentially a mutually attractive force called F between them. And it depends on the distance between them, which is, I have the label here as well, and the distance between them here is R. So you can see that as R gets bigger and bigger and bigger, the objects get farther apart. If this denominator gets bigger, the force gets smaller. And so that means an object across the universe from you does not pull on you very much compared to two objects next to each other. All right, but notice it's G, some constant, this is just a number, times the two masses in kilograms divided by the distance between them in meters, and you got to square it, everything's squared there. Then you get a force, which is in, can you take a guess? The force is going to be in newtons. So this is newtons, right? And then these are in kilograms. And these are in meters. And the units of G are chosen. You can look in a physics book and look at the units of G. But basically you put in kilograms, meters, and then you multiply by G, and out spits a force in newtons. Now, why are we saying all this stuff? Because check out what the force, the electric force, we'll put we'll call it F sub G for gravity, okay? Let's take a look what F sub E is for the electric force. It is some constant called K multiplied by the charge on object number 1 multiplied by the charge of object number 2, and you divide this by R squared. Take a look at these two equations. Don't they look the same? And yes, they are the same. Basically, they're the same form. G is called a gravitational constant. It's just a number. K is called an electric constant. It's just a number. R is the distance between the objects in meters. R is the distance between the object meters. Here, because it's gravity and it's always attractive, it's related to the mass of the objects, how much of the object we have. Here, it has nothing to do with the mass. It's just how much charge. An electron has a -1 charge. A proton has a +1 charge, right? But the actual form of the equations are exactly the same. So let's kind of draw particle number 1, particle number 2 like this. This will have some charge on it, like an electron or proton or something like this, and the distance between these guys is R. So the diagram is the same. Now, the main difference is that gravity is always attractive, but electric charges can be attractive or repulsive. That is a major difference. But besides that, these forces look the same. I mean, obviously, electric force is stronger, but the equation looks the same, right? So how can you get attractive and repulsive forces, right? So the charge here is going to determine that. If you put 2 positive charges here, then you're going to get a positive answer and they're going to be pushed away. If you put 2 negative charges here, negative times negative is positive, you're still going to get a repulsive force. If you put 1 charge as positive and 1 charge as negative, you're going to get a negative answer, and that means it's attractive. So the charges, you know, opposites attract and like charges repel. You just dump the charges in there with their signs, and then the sign of the answer in newtons tells you if it's attractive or repulsive. So why am I saying all this stuff? Because I told you that chemistry is governed by the electric force. It's governed by the forces between all these charges on a microscopic level. But then now I'm telling you that the equations that govern the electric force, we don't have to be an expert in physics to see that this is the same as gravity. So then it allows you to use your knowledge of gravity to kind of predict sort of what's going to happen. And that's why I spent the beginning of the class talking about all of these things that don't seem to have anything to do with chemistry. Potential energy is how far away something is from the ground. It's m times g times h when it's talking about gravitational potential energy. The farther away you are from the planet, the more potential energy you have. The closer you are to the planet, the lower potential energy you have. Because of the similarities between gravity and electricity, the farther away an electron is in a higher energy level, that means it's a higher potential energy. The closer it is to the nucleus is the lower potential energy. Just like things like to fall from high to low energy, electrons like to go from high energy state to low energy state. This manifests itself when we actually burn things, because we break the bonds and then they're allowed to rearrange, but they always go into a lower energy. I shouldn't say always, because you always find some exception, but they almost always go into some lower energy configuration. And when I tell you lower energy configuration, I'm talking about the rubber bands. How strong are the forces? How close are they? How much force is there? That is the potential energy. And the potential energy of these bonds is going to be less than what the sum of what we started with, because the reaction proceeds like this. This is a lot of what governs if a reaction happens or it doesn't happen, right? And then we talked about the idea of kinetic energy. This is the energy of motion. High potential energy, low potential energy at 0. 0 kinetic energy, highest kinetic energy. This means the potential energy is converted into motion energy, called kinetic energy, at the end of the roller coaster run. If you had some reaction where electrons were in a high energy state and they were allowed to kind of combine down and get into a lower energy state, what do you think is going to happen? Well, they kind of crash in, right? Think about if you drop a bowling ball and it accelerates down and smashes into the ground, it kind of like creates heat and vibrations when it hits the ground, right? Well, if you allow these things to rearrange and the electrons crash into a lower energy configuration, you can kind of think of them as crashing in and causing vibrations, and that manifests itself as heat. Not always in every chemical reaction, but you can think of the burning that's going on as breaking bonds, forming bonds in a lower energy, and some of the energy must come out as heat, because when the electrons crash down into a lower energy state, everything's vibrating once it crashes down like this, and then you have some heat that is released. And that heat then goes back to breaking up more bonds of wood and oxygen and continuing the process until your campfire is burned out. And all of this is true because the electric force and the gravitational force have similar forms. So the intuition that we can get from physics applies to chemistry. This is what I'm trying to tell you as the punchline. This is something that you normally don't, well, really, you almost never see it in a chemistry class really laid out like this. But if you do get it, it's like 2 months or 3 months in the future, and you really need to have this in the beginning. I think it's very helpful to know, to break down the mystery. Why is this thing reacting? Why is it doing anything? Why doesn't it just sit there? And that's the reason why, because the energy the nature likes to go from high energy states to low energy states. So in summary, before we solve our problem, if we start in a high energy state, high potential energy, if we allow the system to pull and literally have a force acting through a distance, and now I stop again, then the potential energy is converted into the energy of what we call work. Because a force acted through a distance and now the molecule is stopped again. There's no motion happening. If I allow the rubber band to pull on me and I stop again, I'm not moving anymore. So there's no kinetic energy, but the energy was converted to work. That's just another way of saying, it's another way of manifesting energy when things move, but then they stop again, right? That's case number one. Maybe the potential acts on something and then it stops. Okay, so it's converted to work. But if I pull the rubber band and I shoot this marker across the room, the potential energy is converted to a different kind of energy called kinetic energy, because now the thing is moving with velocity v. And notice that it's 1/2 mv squared. So the velocity actually matters a whole lot more in calculating the kinetic energy because it's velocity squared, velocity times velocity. All right, kinetic energy, potential energy, work. Lots and lots and lots of stuff there. I really would like you to watch this a few times because it takes a while to sink in. Now, I do want to do a couple of really quick problems. One of them is going to be calculation and one of them is going to be conceptual, just to do something in this first lesson here. Here's the problem. If a car with a mass of 1,200 kilograms is traveling at 18 meters per second, calculate its kinetic energy in joules. So this is a straightforward application. If I had to circle the equations that were most important in this lesson, right? This would be one that was extremely important, right? And then over here, this would be one that's extremely important. And then the last one would be this one. That's extremely important. There's basically three equations. Work is force times distance. Potential energy is m times g times h. And then finally, we have 1/2 mv squared for the kinetic energy. So in our problem statement, it says that the mass of the car is 1,200 kilograms. And it's traveling at a velocity of 18.0 meters per second. So how do we calculate the kinetic energy? Well, it's a straight plug-in type of situation. The kinetic energy is 1/2 times m times v squared, right? Which is 1/2 times the mass of 1,200. And then we have the velocity, which is 18 meters per second. If you were not given the velocity in meters per second, you would have to convert it to meters per second. If you were not given the mass in kilograms, you would have to convert it to kilograms. But here everything is already given to us like this. We just times 18 and it's got to be squared, 1/2 mv squared, right? And when you calculate this, you get an answer of 194,400 joules. So 194,400 joules, and then we can just kind of write that in scientific notation and do some rounding with, say, 1.94 times 10 to the, starting here, 1, 2, 3, 4, 5 joules. You can write it any way you want. I'm rounding here because this is a 4, and I don't need to keep all the, I only have my velocity to 3 digits here. So I'm going to keep 3 digits here, 1.94 times 10 to the 5, and that is a unit of joules. Now that's the kinetic energy, right? So this is a car with that mass that's traveling at that speed. Now, if you're at a red light and you're not moving, and I asked you, how much potential energy was used to accelerate the car to that speed? Then you know the answer, because if the car now has this much energy, then that must have been the potential energy used in the gas tank and the combustion to get the thing to accelerate, because all of the energy of motion has to have come from somewhere. Just like the roller coaster, it all came from gravitational potential energy. In the car, when you start from a dead stop, it has to come from the gasoline. And where does that come from? Breaking the bonds of the gasoline and burning it goes to a lower energy state in the pistons and creates heat. And that heat is essentially, you have losses and everything, but that is what's driving the car forward, all right? So that's problem number one, just a straight calculation of kinetic energy. Now here, I'm just going to read the question out and just kind of talk about the answers more than anything. Here we go. For each of the following, explain which has the higher potential energy and why. And so I'll just put A and B. There's really two little things here we're going to talk about. Which one has higher potential energy and why? The gasoline in your car's tank or the gaseous substances coming out of the car's tailpipe. So you have like a box called a car. Gas is in the tank. Gasoline is in the tank. It goes to an engine. A chemical reaction happens. And what comes out the tailpipe? You're not an expert in cars, neither am I, but it's carbon dioxide and water. Most things that burn give you CO2 plus H2O. So the question is, which has the higher potential energy? Well, the answer is the gasoline has the higher potential energy. And you know this because the car's function is to move. And the only way to get it to move is to get energy from somewhere. And the only energy you put into the car is the gasoline. So the energy has to come from the gas. Where? From the chemical bonds of the gasoline. Because when it burns, those bonds are broken down and that energy goes into the energy of heat into the exhaust, and of course that's moving the pistons. The heat is moving the pistons, and that energy is driving the car forward. Now, it's not 100% efficient. You have a gasoline energy is not 100% efficient, not even close to 100% efficient. But that is where the energy is coming from. So because of that, we know the gasoline has to have higher potential energy. Whatever comes out the tailpipe has to be in a lower energy state. In order to get the car to do anything, we have to get the energy from somewhere. All right, and the last problem, which one's higher, which one's lower? Wood in my fireplace or the ashes that remain after a fire? And it's really kind of the same question because we know gasoline is burned. We know wood is burned in a fireplace. So what has the higher potential energy? It's going to be the wood. So we'll say wood. We'll say it has the higher PE. And gasoline has the higher potential energy. Same exact reason. When you burn wood, where is the heat and the light coming from? Well, it's coming from the bonds inside the wood. And when you burn it, you're breaking those bonds, you're combining it with oxygen, and water and carbon dioxide are produced. And those substances, as I told you a few times, are in a lower energy state. So the ashes that are left behind, the soot and all the things that floated up from the campfire, if you add all that stuff together, that's all in a lower energy state. It has to be because the fire released energy in the form of heat and light. And so that energy had to come from somewhere. You can't just have a reaction where you get free energy. So a lot of people say, I'm going to invent a free energy machine. Great, show me what it is, and I'll show you why you're wrong. You can't get energy out of nothing. It has to come from somewhere, right? And in this case, it's coming from the chemical bonds of that wood when they're broken and they reform, making the carbon dioxide and the H2O. So that was an incredibly long lesson. And I don't like making lessons this long because it's hard for me to make a good lesson and it's hard for you to watch a long lesson. But if I did one lesson on potential energy and one lesson on work and one lesson on kinetic energy and then one lesson on the chemistry of how that's relevant, then we would all get lost. You wouldn't be able to see the connections. You have to see them all together. So I really, 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 really encourage you to watch this 2 or maybe even 3 or 4 times. I'm telling you that when we get later down the road and we start talking about how electrons are packed around atoms, it's all going to be about energy. How electrons are transferred. The shape of molecules relates to the energy. You know, how much heat is released in a chemical reaction relates to the energy of the bonds. The bond energy, we have a whole chapter on bond energy, which is all potential energy. All this stuff is stuff that we're introducing now. So watch this a few times and remember it, because as we travel down the road, we're going to be using these ideas. I'm Jason. I hope you've enjoyed this lesson. Follow me on to the next lesson. We'll continue to build your skills. Learn anything at mathandscience.com.